I'm very happy to be back here. As you already indicated, I taught first year macro here for 10 years or something. And I always enjoyed it a lot when I was here, but I felt like I had to cut down on travel, and that's what happened. And but now I'm here. And I also have to say it's particularly nice to be invited to a grad student conference, because that's kind of where the pulse is and where the future is. And I've always seen it as one of my main thing, actually, while looking back, is all the contacts with, through teaching and advising with grad students. So it's great to be here. Also, being invited by grad students is particularly nice, especially since, some of you may not know, but I have the connection to the Nobel Prize, so I always have to question people's the compliments I get and stuff like that. Are they saying? So if it's coming from grad students, then either they're incredibly. But having said that, I think the first invitation I received was from Robin Burgess. So yeah, you were CC'd. Anyway, so I tried to figure out what to cover here. It's a 1 hour talk. It's not 45 pages, it's like 32, just so set your expectations. I will talk about a bunch of things, covering some papers, but I decided to be a little bit more focused on like why macro in this field. Not why macro in general, but I also have to say the beginning of my interest in climate change came when I was at Princeton in 2006, when the Stern Review came out, kind of an LSE product, although maybe it wasn't exactly LSE, I'm not sure. But so we put together a reading group, myself, I organized it, and then Esteban Rossi Hansberg, who kind of later started working on, not immediately, on this in this field, was a product of that. So we had a bunch of students read every chapter of the Stern Review, and that was kind of the beginning. And then I've been working on this since then, and it seems people are interested in the area, and I'm excited that there's still interest, and I think maybe a little bit less among macroeconomists, which is not good, but that's how it is. So let me start by saying it's not about whether we should do something about climate change. I'm not going to question that statement. That's sort of, it's clear there's a scientific consensus that we need to curb carbon emissions substantially. I mean, there's a lot of disagreement on stuff, but I think nobody really claims the opposite, while knowing you're telling the truth. You can, of course, lie and stuff, but I think climate science is sufficiently clear that warming will be significant, and unless we curb emissions, and will give rise to local tipping points, meaning it would be really bad for some areas, and it's particularly in developing countries. And these tipping points, and generally speaking damages, I don't know, we're making big efforts trying to measure them, but I think it's also already clear that they are big enough, especially in some parts of the world, maybe not as a world average. So sometimes when I talk to macroeconomists, I report world average costs of climate change, say 4 degrees warming or some relatively big number. The numbers you get from these various studies that people have are not that huge. So they say, oh, but this is not very big. But I think the point is that it's absolutely huge in many places. And that's more, I think, what the consensus is. But it's also significant on average. So I think in economics in this area has to kind of turn to almost become development economics a bit, because that's where we expect most of the damages to occur. I think policymakers understand that it's not about whether. We know we have to do this, but I think the key thing is it's about how we do it, how we curb emissions. And I think here, we are it somehow. The economists are the people among scientists who, I don't know, maybe we don't know much, but we should know more than physicists and meteorologists and so on about how markets work and so on, how to approach this question. We supposedly understand markets better than others do, and most emissions occur in market economies. I mean, by far. Even China is a market economy in that sense. So emissions occur on the household level, the firm level, and kind of that's what we need to confront and try to understand. But I think economists still have a very limited impact, and that in the area of policy making. I think when I started this, people said, "Oh, economists are ineffective because they propose taxes, and we don't like taxes like carbon taxes." I think so. Just forget about carbon taxes because it's not politically feasible, and we felt a bit sheepish because we felt that that was such a good idea, and we really couldn't see an argument against it. I think now policymakers have come around to a much larger extent, and that's a good thing. The EU's cap and trade system, I think, has to at least some extent been a product of economist thinking. And I think it's very successful, I would say. That it's remarkable. If you don't know the details, I'm not going to show the picture, but the EU's caps on emissions are crashing down towards zero, and within 30 years, unless these things are changed, and they're very difficult to change, we will not be emitting anything net in the EU. And that's remarkable. If the whole world would do what we do in Europe, then we'd be doing very well, I think. And I think it's a smart system and all that. But having said that, I think that's such a small piece of the world that this is an important question still to think about policies. And my main concern is that policies that are not well designed. So here's kind of about design. Policies that are not well designed, they might just not work in the end because they're too costly and therefore become too difficult for politicians to pass in various ways. There is a statement that goes back to Mario Draghi in the ECB, who said whatever it takes to kind of defend the euro system and so on during times of crisis. The next boss of the ECB repeated that in the context of climate change. We should do whatever it takes, but that I don't think is a good idea. Like whatever it takes is usually like, yes, do whatever. And I think it's the opposite. We should think very carefully about what we do because otherwise we'll fail. That's I think the role of economists. That to me is driving my work in this area. So any kind of clues as to how to make our policies better to achieve the goal, to get the how question answer is what I think is the. And then why is macro relevant? So I will touch on this and come back to it. So first, like macro is relevant because the issue itself is global. You can do super well with emissions in the EU, but as I'll show you a graph later, at least according to our simulation models, that will do almost nothing to the climate. So it is a global issue. And when it gets to these how questions, I mean, they're about various policy options, government policies that we have to think about globally. How will these policy options work? We have to, suggest them, evaluate them, see how they compare in terms of human welfare, and that's the task. And doing that quantitatively is what I think macro people tend to do. And again, this is all with the purpose of figuring out, well, which paths should be avoided and which paths seem like good paths to go down. But I have a page here also on the tools we use in macro, because I think that's a little bit, we tend to use models. And one question is why we use models. And so you might, actually my interest in climate change, I told you it goes back to Princeton when we started this reading group. actually, I was contacted by a research organization in the home country back in Sweden when I lived in the US, because they knew I was a macro modeler and they felt they wanted a macro modeler. And I hadn't thought much about climate change at the time, but then I figured, yes, I have the skills, it seems important, so I'll just step up and do it. But I think I don't want to argue for models just because I can do models or because I like models. I think we need them, regardless of who does the work. I think in macro, it's sadly very difficult to find sufficiently good empirical evidence that we can just use empirical evidence to figure out which policy path to go down. And I think if we have empirical policy work that is convincing on an aggregate level, often you need to take into account general equilibrium effects and everything, then I just go for it. It's just that we can rarely just do that. And then we could choose to do nothing. But I don't think that's a good idea to do nothing. I think there's something better than nothing, and that's to use some theory that we think is at least not so bad. So I think this area makes the point even more clear, because it's a super long run issue where we wouldn't expect there to be any really convincing natural experiment evidence. It's also pressing. We have the impression we should really do something soon. Think about it at least very carefully soon. So that's why I feel, I have to. And I was a bit surprised to see that there were several macro style theory papers in the morning, but you told me that was because you kind of put it together that way. So it's a little bit, but so when we work with these models that you find it easy to complain about, then the background is they look so simple and they look so arbitrary, but they're not meant to be arbitrary. We try to make them as good as possible, often focusing on one thing at a time, which of course is not good. So we need to put things together. But I think there's always a reason why we use this model and not that other model. And we also understand very well that there are approximations. A lot of things are missing, and it's kind of gradually learning. And this is like, if you don't understand this, then you can't really do this work, I think. I feel a little bit pressured sometimes, as you can tell from this, this like defensive here. But actually, during the financial crisis 2007, 2008, I taught a little bit in Stockholm, and the students were all over me because Krugman said it's like, this is modern macro is just what did he call it? Some dark ages of the work I do, and they just all over criticizing. So this is a little bit like, it's easy to laugh at the models, but I would much prefer that people come up with ideas of how to make the models better, because I don't think we can just like look the other way and imagine we can't be doing this. We have to do it. So that's why I really like the papers this morning. Wouldn't say each paper should be used for policy conclusions, but we need to add knowledge one bit at a time this way. But importantly, in the title of this slide, it is sort of joint work. We need applied micro for our models to be based on really how the world works. So we cannot just come up with aggregate relationships. We need to make sure they are based on reality. So I have a colleague in Stockholm, or now it's just half time, but some of you may have seen this. I don't know if I showed this in class, did I? But I don't know, in the context of starting a conference, we talked about doing a t-shirt, and he likes to have animals on his t-shirt. So then the question was, what's the macro animal? We need to find a macro animal. And there were all kinds of ideas floating around, and macro is like overview. So at one point, I think the eagle was doing well, but the winner is the giraffe. Because the giraffe has an overview, but it's firmly microphone that is really stands with his feet on the ground. I was later told, I have to say, by a student that when she was like thanking us for the years as she was graduating, that it's also the mammal with like the biggest heart or something. So it is. I mean, this is how I want to view macro. So it's like we do care. It's we're up there. Well, okay, I'm done. Now, integrated assessment models. So what I will do is try to illustrate these points a little bit using one of these models that I am working on and that other people are working on to answer some policy questions, like of this kind, like what is this a good policy, is this a bad policy, and then do some comparisons. And one question is, how bad are different policy errors? So you can make errors, you could misunderstand how the world works, and what's the error then? And then you make an error in some other direction. How bad is that? There we're going to find that in comparing, and I'll be a little bit more clear later, if you decide not to tax carbon, it can become super costly if it turns out that climate change is a big deal. You might think it's not a big deal, you just decide not to tax it. It's very costly. But actually making the opposite error, thinking it's really bad, taxing very heavily, while actually it's not so dangerous. It's not that climate warming is limited or damages are limited. That error is not so big at all. A huge difference, very big asymmetry. And to us, this is, it turned into this type of policy thing. Taxation is a great, taxation of carbon or something equivalent to taxing carbon is a great insurance policy. We don't quite know, there's lots of things we don't know, but we can't go that wrong if we choose to regard climate change as real and the damages as big. Okay. So in particular, this net zero emissions within 30 years, I think it's just a great goal, and it will within the EU do the trick, and I think if the world did it, it would be fantastic, and it would ensure the insurance, even if climate change it turns out not to be so big, kind of per unit of emissions. Another question is, okay, but so maybe we don't tax carbon so much, we just do it a little bit, half the optimal level. Now, optimal, in this literature, there's a lot of discussions about what's the optimal level of carbon taxation. So let me just say this is like an intermediate level of optimal, cut it in half. What happens? Well, that's actually very good. You manage to limit warming substantially, even though it's far from the optimal tax. So even a low tax helps a lot. And the point here, I think, in terms of policy, is that quibbling about exactly how high the tax should be is, to me, a little bit second order. The most important thing is to do something, and even if you go half the way, or even a third of the way, it's a big help. Okay, the next question is harder for people to, well, it's hard for people to kind of take in the answer as I see it, which is, how bad is green energy adoption instead of a carbon tax? So here I'm not saying that green energy adoption is bad, it's good, but if you don't tax carbon and you subsidize green instead, so you just do green energy adoption, then most people think this is great, but when we use these integrated assessment models, it doesn't work. It doesn't work well under the assumptions we make, and we don't rig it. It's likely very bad. Could be that it's better than our models say, but that's more like, okay, maybe our model is wrong, but I don't know. An insurance policy would be to, at this point, be quite skeptical and think twice and reconsider, and try, if nothing else, think about why does the model tell us this, and it told us this. So this is one of the points that, especially in the US, this doesn't go over well. Because the Inflation Reduction Act is kind of all about this. And then another thing which relates to development is how important is it for the tax to be uniform globally? So the PIGU tax, because when you emit the unit, it has virtually an immediate effect on the carbon concentration in the atmosphere around the world. So it doesn't matter where you emit it. So if you use PIGU's idea of taxing with the amount of the marginal damage to others, then that marginal damage to others is the same everywhere. So you should have the same tax everywhere. But in many developing countries, they say, well, this is not fair. You guys could develop while not taxing carbon for hundreds of years, and why should we now tax carbon? And regardless, I think, of whether you agree with that philosophical statement, it's interesting to see, okay, what if we allow some countries on the lower level of development to not tax carbon? And that turns out to be not good either. I mean, it's not a catastrophe, but the amount by which we need to raise the tax elsewhere to reach the same temperature target is so large that I don't know, would be much better to use the money you lose from doing this to just compensate in a number of ways. These countries that would enjoy the low tax, they would enjoy the low tax or zero tax on carbon, but not so much that it really compensates for the losses for the world. So there must be a better policy than doing that. That's another conclusion. I mean, these are things that none of these answers here are what we expected. I guess we tend to display, there's a certain bias. We tend to report the answers that are interesting in the sense that they surprise us. Of course, there's a number of other answers you get along the way that are not surprising. I think almost all of these were surprising to us and kind of not by design. So I'll make most of the points, not the very first one, but with this model that we have now that's called climate policy in the wide world. I don't know if you can use that expression, really, the wide world, but I like it because it reminds me of a Cat Stevens song that I listened to a long time ago, which is another kind of, it's wild word, but anyway. But I think you understand, like in all of the world. So properties of IAM. So I think here, now I need to kind of list what I think are minimum assumptions for a model to be taken a bit seriously, okay? And I'm not going to go through and show evidence, but I think it needs to be somehow best practice and quantitative. So best practice in economics, I think it is some sort of growth model. We've gone through, Solo came up with a new classical growth model. There's been a lot of work on growth, empirical, theoretical, endogenous growth, this and that. At the end of the day, at the moment, I think that some form of growth model is still the way we think about long-run growth. In this case, we also want to have it be regional because it's relevant to see what happens in different places as we implement policy. I think the model, unlike Solo's, because Solo, I once got a letter from Solo, it's like a handwritten letter. There was a comment on a paper I published with Tony Smith, where we talked about optimal saving, and he said something like, "Oh, as you know, I've never believed in optimal saving." And it was like, "Thank you, it's very interesting to read your paper, but I don't like optimal saving." And I mean, I didn't know what to say, so we didn't respond. But it is a model with optimal saving. Having said that, optimal saving or not doesn't make a huge difference. So this is not something to get excited about. This is wrong or this is right. Roughly constant saving rates. Solo assumed constant saving rate is kind of not a bad approximation, I think. He did use optimal behavior for firms because when he backed out Solo residuals and so on, that was all about perfect competition, price equals marginal product of input of outputs, and so I think that, I mean, having markets in the model is important, okay? So market economies, how firms and consumers respond to policy and to the climate, I think we need to build into it. The model should be reasonable on a micro level, and that was the giraffe thing again. No crazy assumptions about elasticity. But again, do we know what the elasticities are? Not necessarily, and that's why I think we need to do a lot more work. It should match historical data, I think. So I think the growth model is kind of that's kind of what it was constructed to do, and I still don't know an alternative. So this stuff, as we realize, is strikingly similar to climate science practice. So we have talked a lot to climate scientists throughout the years, in Stockholm primarily, but also some like big shots from other places, just to make sure we don't misunderstand results. And this is kind of what they do also. They thought that our models were very simple, incredibly simple. How can it be so hard to compute your model? They told us, well, why can't you deal with more than 4 state variables or something? But then they didn't realize that our agents or our particles are forward-looking. So what happens today depends on what happens in the future. So they think, oh, 20,000, 100,000 particles, no problem. I can do more, give me 1 million. But then when you have to kind of factor in some form of forward-looking. I know you talked about this in a famously quoted speech or something. All my colleagues talk about it, Ben. But like, maybe expectations are not fully rational. I'm all with that point of view. But I think they are to some extent forward-looking. And as long as they are forward-looking to some extent, you're kind of into this difficulty in dynamic models. And when they understood that, actually, they were like, they clammed up and they haven't insulted us since then. So these climate people. So I think we have to respect the restrictions we work with in different fields. So I think we have an integrated assessment model, which I find rich, non-trivially quite useful. I have a note here, which is not everybody agrees. That's because a little bit early on in the literature, Pindyke wrote an influential piece where he said that these models were not useful. I think it regards like, what is the optimal tax on carbon? That turns out to be robustly not so dependent on so many things. So do you really have to put together a huge model to calculate something which is relatively straightforward? Maybe not. But I think the point here is, it's not about the optimal thing to do. It's about looking at different policy options, including some stupid ones, ex post, and see how do they play out in the marketplace. That's, to me, and for that you need models that deal with markets that are not perfect and so on. So that I think that use of this model is fantastic, and so I totally disagree with dismissing the framework. Climate facts. I will not show you pictures. I might at the end if you have questions, but climate fact number 1 in the IPCC just is that there's shockingly an approximately linear relation between cumulative past, undepreciated cumulative past emissions and the climate outcome in the form of temperature. So the more you emit, the more the temperature goes up. It doesn't matter when you emitted it. It's very strange, but that's how it is. This is an approximation that comes out of just a lot of modeling efforts, and it's a new discovery in climate science. Well, new, but like 15 years old. But it's now consensus. So this, for example, if we know we can't go beyond a certain temperature in 2050, we can calculate backwards how much we can emit. It doesn't matter when we emit it. That's why we use a term called carbon budget. We have this budget, we can't emit more. If we emit this amount, we hit that temperature. Now, there is uncertainty about exactly what that coefficient is, and the uncertainty is quite large. So you have to be aware that when you do these calculations, you should kind of look at the 2 endpoints of a reasonable interval, but the linearity comes out in all their models. So that means indirectly that there's no global tipping point in these frameworks. But they also say in the IPCC report that you can't completely rule it out. So I think that's another reason to have like do something pretty aggressive toward emissions, so that we also potentially avoid this problem. Local tipping points, they are like, there's lots of local tipping points, and they are the ones that can be extremely costly in lots of places. Okay, fossil fuel reserves, I think the issue there is coal is super abundant and it's a main threat, along with non-conventional oil and gas. I mean, this is a little bit in contrast with an earlier presentation, which said that also conventional oil is very problematic. And I think the view here is a little bit of a contrast, but let's not focus on that contrast. I think this is still true. Coal is by far, we have a lot more coal than we have conventional oil and gas. I think, we have also lots of things to learn. And here I think is where I know the least. Energy technologies, energy input options around the world. How much does it cost in different places to use different types of fossil fuel and green energy? It's a key question that is a key input into these models, and we need to kind of improve our understanding. And then damages, I think here the key thing is that it's just the heterogeneity. The overall level, I think, there's disagreement, but I think the heterogeneity in damages swamps the average effects anyway, where poor countries are hit really hard. I think we should also think about the policies in place today, but roughly speaking, policies in place today, except for the EU, are to not tax carbon. There's green subsidies in lots of places, especially the US, but in terms of carbon taxation or the equivalent, it's just us doing it. Okay, so now I have 25 minutes roughly, and I'll now show you the specific model we most recently worked with. The focus is the wide world, maybe the wild world also. Again, it's a neoclassical growth model. Apologies, it's a simple model, but I think it's the only one economists managed to come up with to replicate the long-run data. It has carbon cycle and climate blocks that we took from Nordhaus really, but they didn't quite work. So there's a recent paper coming out in Restud that shows that a slight alteration, not our paper, a slight alteration of Nordhaus's framework will actually deliver what I told you, this striking effect of linearity. So you just fiddle with some of the parameters in that framework and you can get exactly that. Even though there's depreciation of carbon in the atmosphere and all kinds of things going on, that you still get this linearity. And that's this point. So these blocks are updated to reflect the latest climate science insights, and that's possible. We use very high geographic resolution. There was a paper this morning on a similar framework. This is in a way strikingly similar. The baseline here is 1 by 1 degree, with each cell assigned to a country. And so we get rich local predictions. And we designed the model so that it would be simple to solve. I mean, I have over the years worked on simple models and difficult to solve models and try to solve difficult models and stuff like that. Right now, I felt like there is a way forward in this framework that where you don't forego so much realism and you can still claim it's quantitative. And so this is, in the beginning, we even solved it on Excel, but that's a little bit like insulting to some people. So we are solving it in MATLAB now. We went to the high level of sophistication. But I mean, I just think it makes it easy to use for beginners, and that's a plus, I think. Do we have weaknesses? Like, we have a lot of weaknesses in this model, and I'll be clear, open about. By the way, I am happy to take questions throughout, because that was and you usually ask a lot of questions. So, but anyway, so feel free to ask questions. So the model consists of all the countries in the world. That's a déjà vu. Each country J is divided into regions I. These are the grid cells 1 by 1. They all use capital, labor, and energy to produce a final good. That is the same final good as in Europe. It means like one good per country, and they're all the same. We actually don't allow world market for capital. So we have interest rates that are specific to countries, but we have reasons to believe that that's not a big deal, that restriction. Most regions cannot produce oil, so there is an international oil market where you where price of oil is determined. Those cannot. There are countries that produce oil, but and we make, for simplicity, we assume that they can only produce oil. They can't produce other things. So it's in fact, in practice, when we model Russia, we divide Russia up into a chunk that only produces oil, and then another chunk that doesn't at all, just to kind of get the numbers right. Okay. And there's no further international trade, because the only thing that would be traded except oil would be consumption over time, since it's just one good, and that's so no further. So within each country, there's coal, there's green energy, and they are produced locally. Now, our assumption within each country is that people can move costlessly, within borders. So this is a bit like your paper. I mean, you're really assuming that. I think people have different shocks, but here they all have the same wage, essentially. People are the same within each country, and that's just to simplify. So because we have a long time period, year to year, this would be a very bad assumption. But for over a longer period of time, I think it's not so bad. We assume perfect competition, and that means factor prices are required to be the same within each country. You'll see the details in a moment. I will not show too many equations, but you will see this part. Consumers are rational, but as I said before, I don't think it's like a super big deal to depart from it. I'm opposite. So there are really two decisions. One is where they will work, and they move so that wages become equal across the different locations within the country. There's going to be migration pressures everywhere. I'm not going to report them here, but what you can do is you can, at any border or any bilateral country comparison, you can see how much would a person gain from moving if they could move. So we can measure off of this type of model migration pressures. And that's interesting in itself. And we haven't done it here, but it's something nice that you can do. And we assume population growth because that's that's an important thing. And we use UN projections that are available for each country in the world going forward and until for a long time. And there's a finite amount RJ in country J of oil. What else? Governments, they are very passive. They basically, to the extent we use taxes, they tax emissions, and that's it. So we don't have other distortionary taxes here. So firms, okay. So here we clearly have weaknesses. I'll discuss this a little bit. There's one sector that produces the final output, and then there are other sectors, but they produce intermediate inputs. So intermediate inputs here, they are intermediate energy inputs, and we make the assumption that the final output good and the energy input goods are all using the same like isoquants, but they have different TFPs in front, which means that those TFPs you can show become also relative prices, and so the TFP here is exogenous, so then we have like exogenous relative prices. We can make all kinds of assumptions about the relative prices here, and that's, I mean, it's a trick. It's something that makes the model simpler. But anyway, for the sectoral, different sectors within a country, final output versus energy. So here is the in region I, in country J, this is a TFP that I'll show you in a moment. It uses capital, labor, and energy. The energy share can be different in different places. And then we have it's a phi, right? Am I saying this wrong now? Sub J, so this is less than 1. I asked the question also in this previous talk here. This is less than 1, so this means crowding. So if you could move freely within a country and this were 1, everybody would go to the highest A. So here there would be more people living and working, more capital, more energy used in the highest I within a country, but it wouldn't go to an extreme. So we actually look at the data and estimate this from the cross-sectional distribution of output and people. within each country, given that we have this one-by-one cells from Nordhaus's GE-econ data. So that's the fixed factor. And this particular framework with Cobb-Douglas and so on actually aggregates. So you get an aggregate production function for the country J, where the I things are gone. You can easily see here how you can also put in various wedges, but we didn't do it here. So wedges are very, I think, reasonable in a bunch of contexts, but here no. And under Cobb-Douglas, full depreciation on capital, which is okay because we have a long time period. So we can think of capital as on average depreciating almost fully within 15 years or something. Then, you know, we just assume there's full depreciation. So logarithmic utility full depreciation and Cobb-Douglas gives us closed form saving rates that are not constant because they depend on population growth, but you can work them out. Now, again, this is not so key because I think if we assume constant saving rate without it being fully optimal, it would be okay also, like going more down Solo's path. Okay, but I do want to talk about Cobb-Douglas because we always assume, I always felt this was a little bit embarrassing. The macro people always assume Cobb-Douglas, but I realized lately that when many of my applied colleagues do a theory, it's also Cobb-Douglas. So this is like the only function we know. But it's not the only possible choice. So I will get back to capital versus labor, but I'll talk about, you know, why is energy Cobb-Douglas, or is energy Cobb-Douglas? It came up in the in a paper earlier, the one on monopoly, and so here is data from a paper of ours. So that's why the data set is short. But red is the fossil fuel, the weighted average fossil fuel price in the US, used in the US. And the blue is the share of gross output that goes to energy. And you could see here that, I mean, here's the oil shock number 1, oil shock number 2, and then there's lots of fluctuations. They go together, like in lockstep. When does that happen? If the production function is almost Leontief. If the elasticity is very close to 0. Which is what you saw the estimate was. Where are you? It was like 0.12. I mean, I'm going to use a slightly lower number here, but they are very similar. And it's because of this, essentially. Over time, this is what you see. So if you nest capital labor there as a Cobb-Douglas for now, with energy, with 2 specific factors, AT and AAT, and you make epsilon close to 0, I mean 0.12 or 0.02, as I'm going to show you, then actually you could use input prices and input quantities a la Solo, except we use this production function. We assume this is correct. Solo just assume constant returns to scale. We're going to assume this CS is correct. Then we can back out what this is and what this is. And then you see, this is, the blue one is AE, so the energy augmenting, energy saving thing that's measured here. These are 2 regression lines, but the remarkable thing is how this curve changes. It's not doing much over here because, I mean, I'll just say it in words, because here fossil fuel is cheap, oil is cheap, oil becomes very expensive. Then it looks like in the aggregate sense, there's huge saving on the expensive thing, which was a question that came from the back, and I think that's absolutely head on. There is saving on the expensive thing, and this is something I call directed technical change, or others call that. So the AAE adjusts to give what? And then I argue approximately Cobb-Douglas. Well, you know, we had a Cobb-Douglas here, and the sum of the idea is in the short run it's CS. In the so it looks like this, but when A, E, and A change endogenously in response to prices in reduced form, if you look at the share here, you see that the price goes up slightly, the trend, but the share goes down a little bit. But that means the share on average over a long period of time is almost constant. So I think for me, with 15, 20 years, assuming the share is constant is not so bad. That's why we use Cobb-Douglas. The second thing, capital versus labor. I have another line of work that's not directly about climate change, but I feel I have to comment on, which is in development economics. Okay, poor countries are mostly about agriculture, and capital labor shares kind of behave a certain way in agriculture. So first I'm just going to show you, this is just GDP per worker 2005. Here are all the countries, and this is agricultural employment share. This is not a surprising thing. The rich countries have very few people in agricultural sector, and the poorest countries have most people in the agricultural sector. But remember, I said that we use a final good that is the same as in the whole world, and maybe we shouldn't. Maybe we should assume that poor countries produce a different good, namely agriculture, to a large extent, and I don't know, countries in between, a mix, and so on. So we set out as a separate project, me with other people, to study aggregate data on agriculture. And here's just one graph from that paper that was somewhat shocking to me. So the x-axis is still GDP. So here are the poorest, here are the richest countries. What you see in the dashed line here is the relative price of capital divided by the relative price of labor. So R divided by W. So R is roughly the same in all countries. W is very low in developing countries and very high in our countries. So R divided by W is here, like it's 20, 30. Over here it's 1, so it's normalized to 1. Meanwhile, the shares, the ratio of the quantities, capital divided by labor, goes from here 1 to actually a number much bigger than 30. Here it's 256. I mean, it's not surprising that it's down sloping here, upper sloping here. It's expensive there. You use less capital here. You use a lot of capital here. What's surprising is that it's such a tight relationship. It's a log scale on both sides, and it's a small step away from saying there's some cross-sectional elasticity here going on. When you change the relative price, the relative quantity, just take a CS and this just jumps straight at you. Now, I'm not saying that therefore we have a CS QED, but it's a huge, enormously striking fact to me that it's so log linear in both directions. And so what we could do here is that we realize that the capital share, capital is used more. The capital share is not the same here as here, because remember this went from 30 to 1, and this goes from 1 to 256. So there is a systematic change in capital versus labor shares. So we could use different alphas in our model just to kind of capture that at a first pass. That would be fine. We could still solve the model. We can also use, this is like, I don't know if it's an exercise now in the first year PhD, but actually if you have a CES production function and I don't say it here, but if you have, instead of logarithmic utility, you have utility function that has another elasticity substitution that's the same as this one, and you also have constant saving rate. But again, it doesn't matter. Saving rates we can assume are roughly constant anyway. But we could kind of go to a richer framework. And so here I'm a little bit like, it's research in motion. We also see in that other paper that for non-agriculture, for manufacturing, the elasticity you get from just looking at the cross-section is actually remarkably close to what Douglas. So it's sort of when we're looking around at cross-sectional data, which we know is a problem, but anyway, the numbers are so striking that we have to think about them more, I think. All right. The results are quick to go through, but I just want to show you the last bit of the model, which is this energy composite that all the regions use. It's a composite of an oil thing, a coal thing, and a green thing, where the oil thing might contain fracking or shale or something like that. So it's kind of something new that is comparable to oil. We assume that this row here is 2. When we started this work, we went out and looked at the meta study that went through all kinds of estimates for elasticity substitution across different energy inputs. The average in that study was 0.95. So for years we were using 0.95. People just can't take it. So we increased it to 2 because people feel that it's more substitutable. I'm frustrated to say that I don't know what the number is, and I don't know maybe this is even the right way to measure it with this type of CS. It's a weakness in our work that this is, I think, where we are a little bit on deep water, where we need a lot of help, I think, in particular. And I think there's huge heterogeneity by region, how energy supply comes about, going like from Iceland to other examples, funny examples. We use, it's an integrated assessment model, so we build in damages into the TFP term. We assume different growth rates for different countries, again following some projections that there's technical change or catch up in the world, where India and China will continue to catch up, but for a while, until eventually all countries grow at the same rate. And then we have this, so we have a region-specific thing that is constant over time. We have country-specific thing here that's changing over time. And then we have this climate change damage. What do we assume? Forget about the functional form, but this is a U-shape. Someone here mentioned U-shape before, or I mean, the damages are U-shaped. This function gives you that. This is a damage function of local temperatures. It is like a sweet spot of temperature. We make that assumption following a bunch of papers in the literature. How do we get the local temperatures? By what's called statistical downscaling, where basically this is a model based on simulations of climate models, where as the global temperature average is moving away from the pre-industrial and rising, each little region has a coefficient, linear coefficient, that you can use to predict what's going to happen there. So different regions have different propensities for warming as a function of the global warming. And this maps tells you that. So 1 is the average, and you can see that actually coastlines warm less, but they of course have other problems with flooding and stuff. So this is just a picture of that downscaling that comes straight out of climate science. Here are the temperature graphs. So share of global GDP, if you plot it against temperatures, this is in 2005, I think. So you can see that like most GDP is produced where you have something a little bit above 10 degrees. This is the plot of population, and then you see that, yeah, there's a lot of people there, but there's also a lot of people over here. I don't know where Rio is exactly, but it's like over here someplace, much warmer than in other places. So somehow, at the end of the day, these damage functions are somehow calibrated to this type of information one way or the other. And this is the damage function. I mean, this is the TFP, so it peaks at 11.6. Okay, parameter selection, I'll skip that. I'll skip this too. This is just to show that our model generates emissions that by big region looks kind of like the data. So policy experiment 1, we assume that the climate implies a lot of warming. In fact, we picked the worst scenario of the IPCC interval. So the biggest climate sensitivity, and that the global damage at the same time are like the worst in some interval. And then still tax at 0. This is an error. And when you solve this type of model, you see that that's actually very bad for human welfare, something like a Great Depression, at least on average in the world. That is permanent, because this is like permanent. So it's like Great Depression for the world as a whole. Just imagine the poorest countries. So this is terrible. It's a mistake. Another mistake, set taxes according to that really pessimistic scenario, and see how that policy does. If actually you're completely wrong and it's like Trump is right, Okay, then what happens is that, yeah, that's costly too because it's an error, but the cost is like very small, shockingly small. And for a while we didn't quite understand what's going on, so we had to construct the static model and analyze it. And now we did, and we convinced ourselves that it's not just like, it's not a computational error. There are deeper reasons. Anyway, and since we're uncertain about climate and the costs, taxing carbon, I mean, it's obvious to me that we should proceed in a pessimistic way. This is coming out a bit like using a max-min type of policy approach without actually doing it. We're not doing any of that. We're just saying, suppose we're wrong this way, suppose we're wrong that way. They look very different, so let's go this way. Okay, policy experiment 2. They are quick. I mean, 3 minutes, but I can do it. Consider a modest tax, $20 per ton of CO2 at the initial date, and then it grows at the rate of world GDP. And this is what happens in various scenarios. So the global CO2 tax is the dashed line. So this is 2005 because that's when we start the model. But basically, that leads to warming of a little below 3 degrees, but by 2140. So this compared to business as usual, or compared to the purple line, which is that we do very well in the EU, but nowhere else. So the EU doesn't matter. That's the difference between these two. So this is doing nothing, the blue. This is doing nothing in the rest of the world, but doing really great in the EU. And then this one is if you actually don't tax oil and shale and stuff. So it turns out those things matter. So you get half the way, but so you should really tax all of carbon, and if you do it even in a modest way, you drop from there to here, and that's what I meant by it's very helpful to even do it a little bit. And this is like let's forget about the details, but what we see here is like that's the damage function. This is if you don't do anything. So remember, this is the TFP, the inverted U. This is the population, and what happens with a lot of warming is that the population is like moving right. The density of population is moving to the right. So people who used to be here, they are now much further down on the TFP curve, and they're losing a lot. That's kind of how to read these things. And you could see how different policy scenarios affect different parts of the world. We have maps as well. Policy experiment 3. Now we do non-uniform tax. I've already explained the background. We quantify. So again, start with this modest tax of $20 per ton, and then look at the results of letting poor countries defined to be 25% of global GDP per capita have very close to zero tax instead of having the $20 tax. And let the rest of the world increase their taxes so as to hit the same eventual temperature increase as you saw in the graph. So we don't want to change the temperature goal, we just want to shift the burdens. So that means actually that the tax rate has to go up by a factor 20 in the rest of the world, and because it's essentially zero for the other ones. And here are the results from that. Income weighted losses for different regions. For the world as a whole, it's a loss of over 4% of consumption. You see that Africa gains as a whole. Within Africa, within these places, there is going to be winners and losers. But regions, aggregated regions, you see the losses are over here. There are some gains in Africa. But this is the sense which is a relatively big loss for the world. I do want to do the last one, right? I have a minute, hopefully. Which is, as I said, it's the most controversial one, at least in the US. So they have this IRA approach, which is, I think, it's a good thing, but basically mostly focusing on making green technology cheap. So given our model, we can do the following. We compare two scenarios. One in which the relative price of energy exogenously becomes cheaper and cheaper by 2% per year. So, and that's free, just like we don't even have to do research. It's just getting cheaper and cheaper and cheaper. So after 20 years, 40 years, it's at really much, much cheaper than it used to be relative to fossil fuel. So it's a technical change that hopefully you could engineer. Here we're just giving it for free. And we're looking at the comparison between taxing carbon and doing this instead of taxing carbon. And we look at two cases. One is where US-like IRA policy generates fast green technology growth, not only in the US, but also elsewhere. So this technological change spreads. And then another case where it doesn't spread outside the EU and the US. And here are the results. So the carbon tax I showed you, it ends up here. This is again the modest tax. So of course we could have a tougher tax, warming by 3 degrees. And if you just do green policy in the EU and the US, I mean, it's almost like you didn't do anything. If you do it in the whole world, you cut a few degrees there. What is the problem? The problem is green technology is great because it makes us consume more energy. And that's good for production and it's good for humans. But for climate change, like total energy consumption is not the key thing to look at. It's fossil fuel consumption. How good is green technology at competing out fossil fuel, kind of by itself? And these, I don't know, these functions we use, these estimates of elasticities and so on, and the initial prices of how much do they cost on average today. I know there was a comment earlier today. There are places where solar is cheaper today than alternatives. But when we do kind of a world approximation of prices today, there's still a big advantage of fossil fuel. So if we just do green and hope that fossil fuel will go away, I don't think that's a safe option going forward.
Just a question. I was the one who said that.
One question.
But how does this square up? I mean, in 2/3 of the planet, according to the latest data, solar or wind is cheaper than fossil fuels. So what is happening in your model?
It's more like there are lots of facts out there. I'm happy to sit down afterwards and like talk about exactly what does that refer to? Does it refer to green technology being really available in the US for all the intensive use of energy and manufacturing, the same in Europe? I don't know. You've seen what goes. There's no mystery. What goes on in our model is we have this aggregate technology with elasticity substitution. I think, as I said there, we'd like to bring it down on the regional level, and it could be that even many regions are better at green than carbon. But I think the evidence out there, as far as I understand it, is that it's not that easy in an aggregate sense to substitute. It's easy to imagine, like if you have an electric machine, you don't care where the electricity comes from at some point. So it sounds like it's perfect substitute, but I don't think that's how it works. So, but
I think it's that slide where you said maybe you need help, like on the substitution. I think that's maybe changing quite quickly with storage and managing intermittent generation.
I think one aspect of storage and intermittency is precisely the elasticity might be going up. But this is why I said we used estimates that were 0.95 because that was the average out there. Now we're up to 2. I don't know, we can move up to 10. I don't know, but it's like at some level we need to ground our numbers in something a little bit better. And it's not that I want to drive the results one way or the other. This is still worrying me. So even if you say, is that really right? I'm still worried because I think this is a critical thing for evaluating IRA policy.
Thank you.
That's all what I want to say. Not that it's a bad policy. Yes. Okay, that's it, I think, because I just had the concluding slide, which is like macro is great, and then this is just for policy experience.
So we lots of opportunities to ask that very challenge. Okay, so are we gonna go at once?
Yeah, we're going to pass it.
Yeah, so let me just, people who are in the back can read it, please. So everybody standing up. So let me just, as we set up the panel. I see your turn.
Yeah, exactly.
It's like,
I think that last point is the key one, whether or not the substitution has actually become stronger.
it's fine.
Fine.
It's fine with that.
That's what's happening. I think the expression is still